Everybody, it's Bill from the Auckland Astronomical Society here. Just warn everyone, Steve, who's hosting the convention, on staff. Are you there, Steve? Yeah, yeah. It was just the connection dropped out. Possibly something. Hi everyone, sorry about that. We dropped off the air there. There's a thunderstorm around, and I don't know whether that caused a disconnection, but we're away again. So hopefully neither Steve nor I will lose power during this talk, otherwise it will get interrupted. So I decided to do an extra talk about variable stars, as we weren't able to do film night last week. And there's been a bit of activity in the public, or at least the astronomical public, with the Nova RS Cepheid having an outburst recently, and that being a recurrent nova, and that I thought prompted me to come up with the idea of doing a talk on variable stars. So we'll get into it. So a bit of a historical thing. It appears that Aristotle, who was probably the most influential of the ancient Greek astronomers, believed that the heavens were fixed and wasn't accepted by everybody, but that stars were some kind of condensation of a perfect element called the fifth element they called ether. And the planets and moon were also made of a similar substance, but were attached to spheres that moved inside the sphere that the stars were fixed on. Now, a lot of observers of the sky were familiar with comets, and they obviously changed quite radically over the time they were observed, appearing and disappearing. But that was sort of got around by claiming that they were atmospheric phenomena rather than something related to the stars or the planets. So it must have been the case that new stars, or nova, as they were later called, and then supernova, were observed from time to time, because some of them appear quite bright, and any sort of observer of the sky would have noticed them. But there isn't really any convincing record that still exists. Now, it's possible that's just because there were records made, but they've been lost. Of course, that's a problem with historical documents, is that unless they're in some form where they keep getting copied, or as a durable form like clay tablets, things can get lost. The furthest unequivocal record was a guest star recorded by Chinese astronomers, known as recognized today as being related to Supernova 185, SN 185. Also observed in 1054, 1572, and 1604. The last two were observed by Tycho Brahe, and 1604 Johannes Kepler made a lot of observations of it, recording change in brightness over time. And of course, he was also involved in the Copernican movement along with Galileo, and basically challenging the idea that the stars were fixed and that the everything rotated around the Earth. So we came to the invention of the telescope, and that meant that stars of much fainter brightness could be seen. And the record of a star that regularly changed its brightness was recognised by 1638 by Johannes Hallwater, who noticed Omicron Ceti was varying in a regular cycle from second magnitude to well below what you could see with the naked eye. So you needed a telescope to see it when it's at its faintest. And this was occurring over a period of 332 days. And it was given the name of Myra, meaning the wonderful, because this was the first really documented case of a star varying in such a regular fashion. And you can see on this stellarium rendering in the constellation Cetus the Whale, it's readily visible from both hemispheres. And you can see that it's actually in the spring sky is going to be visible. Let's move on to the next slide. Another thing that happened interesting that was easily seen with the naked eye was the star Betelgeuse, where you can see here two images taken of it a couple of years ago, where the brightness changed considerably. Now, Betelgeuse with long baseline interferometry, it's actually possible to resolve the star as a disk. And you can see here that something was attenuating part of the disk of Betelgeuse, causing it to noticeably dim. It turned out that it was observed in infrared wavelengths, and the dimming was pretty minimal in infrared, so that led to the conclusion that it was being caused by dust intervening, probably circumstellar dust, possibly that had been thrown off by the star. I'm not sure what the latest theory of it is, but that's the most likely explanation. So this is a type of variable called an extrinsic variable, because it wasn't the star itself that actually dimmed. It was caused by something external to the star, even if it happened to be some material that was thrown off by the star. So we come to the different types. So you have intrinsic variables, which is a variability caused by some kind of change in the star itself. So the star is pulsating or undergoing some other kind of change. And extrinsic variability, where it's caused by some kind of external property, such as two stars that are eclipsing each other, or a dust cloud, or some other phenomena. Rotation is referring to stars that could have sunspots, very large sunspots, large enough to cause a drop in brightness that's measurable. Not sure that I agree that that's external, because the sunspot is a property of the star itself, of the star's atmosphere. But anyway, that's apparently the way it's classified. So the common kinds of intrinsic variables are stars that pulsate in some way. So this is because they're a bit unstable, and so the radius is expanding and contracting. As it expands, the star cools, and color changes, and the brightness changes as they undergo these kind of pulsations. We also have eruptive variables, and these are stars that have some kind of outbursts from their surface, like a solar flare or mass ejection. Obviously, the sun does this on a smaller scale than a lot of stars. Red dwarfs are particularly known to have eruptions of flares that are a decent percentage of their overall brightness. And the other kind is cataclysmic or explosive variables. So stars that undergo a cataclysmic change in their properties, such as novae and supernovae. So the extrinsic ones are kind of interesting. Some of them happen because of just an eclipse. They two stars orbiting each other, where the two stars' orbital plane happen to line up with our line of sight. A well-known one of these is the star Algol. So you can also get a form of this, which is a planetary transit, and modern instruments such as the Kepler spacecraft can detect very small changes in the star's brightness. So, and this can detect a planetary transit if it happens more than once and it's happening on a regular cadence, then you know that it's something like a transit of a planet across the star. And a few thousand planets have been discovered from this phenomena. We have gravitational lensing, where a chance alignment of a star with a foreground and background object. The foreground star acts as a gravitational lens and amplifies the background of a background star, the brightness of a background star. Studying of these is done by some members of the society, and is another method of detecting planets. If the light curve of such a chance alignment of two stars is just a simple Gaussian, then there's nothing interesting happening there. It's just a chance alignment, but sometimes you get little anomalies in the light curve that can be caused by planets orbiting the foreground star that basically distort the lensing effect. Another kind that was mentioned before, a variable due to rotation with extremely large sunspots, which apparently occurs on some stars, particularly ones that are rapid rotators. So if we go to the Hertzsprung-Russell diagram, which plots the absolute magnitude of the star versus its spectral class, or temperature, if you like, you can see where on this chart where the different kinds of variables exist. You've got flare stars, which are the red dwarfs, white dwarfs, and dwarf novae are basically types of variable stars there. In the upper end of the main sequence, you get these magnetic variables, massive stars with powerful magnetic fields. T Tauri variables are really young stars that haven't settled onto the main sequence. And then you get the other giants, common ones, Cepheid variables, and RR Lyrae variables. And these supergiants tend to be quite unstable. They're getting towards the end of their life. And so the type of nuclear burning they're performing in their cores becomes unstable. So you don't get like main sequence stars are generally close to equilibrium. And so here's some of the types. Luminous blue variable, which is a very massive star, maybe 60 to 80 times the mass of the sun or greater. Then you get your long period variables, such as the Myra we mentioned earlier. Two types of Cepheid variables, RR Lyrae, T Tauri, and these are all due to pulsations of some kind. Then you get the nova and recurrent nova, and they are of a type known as a cataclysmic variable. And Similarly, dwarf novas, we'll go into a little bit on what those are, and of course supernova. And unlike the others, a supernova can only happen once because the star is destroyed. Okay, so hydrostatic equilibrium was mentioned. So this is in a star where the outward gas pressure is exactly balancing the gravity of the star. So the processes in the core are a really stable rate of generating heat, which creates the gas pressure, and also photons in the core from the nuclear reactions provide pressure resisting the collapse of the star. And in main sequence star, this process is such that it's quite stable. So the stars, for a long time, like in the case of the sun, will burn for billions of years in this state without doing any dangerous pulsations. Well, dangerous to us anyway, being so close to it. So another type of variable star, which is a fairly massive star, getting to the latter stage of its evolution, is called a Cepheid variable, named after the star Delta Cephei, which was the first star that this type of pulsation was seen, and they can range from 1 to 70 days. Now, the interesting thing about these is that the period of rotation is related to the absolute magnitude of the star. So this star, by measuring its period, you can use it as a standard candle. So pretty useful as one of the early ways of measuring distances, where parallax was limited to relatively close by stars, a Cepheid variable. If there was a Cepheid close enough to get a parallax measurement, you could use that as a standard to estimate distances to Cepheids that were further away. And of course, famous case of Edwin Hubble, who detected a Cepheid variable in the Andromeda galaxy, and knowing the period, he was able to estimate the distance of the galaxy. They're quite good candidates for projects to get involved with because they have a relatively short period. You can visually estimate the magnitude if you've got a telescope. Some of them are quite bright. If I Delta Cephei itself, if you notice that the magnitude is well within the visual magnitude range, so it can actually be done with a just naked eye or binocular observation. Another type of pulsating variable is the RR Lyrae star, and these have a much shorter period than the Cepheids. They're a white giant star, so they have a fairly high surface temperature. They tend to be less massive than the Cepheid variable stars, and the amplitude of variation is between 1/3 to 2 magnitudes. Just a bit of a quick explanation of magnitudes if you're not familiar with that. It's based on the way the ancient astronomer Hipparchus ranked stars from first magnitude to the brightest stars down to 6th magnitude for the dimmest ones that could be seen with the naked eye. So that's basically a difference of 5 magnitudes between 1st and 6th magnitude. So the system was adapted to a more scientific method where you could actually measure the brightness of stars and use this as the base of the system. So for example, if you're looking at the sun, magnitude is nearly -27. So you extend the scale so that things that are brighter than the 1st magnitude, you go to magnitude 0 and then to negative magnitudes. The moon roughly -12, Sirius -1, something like that. And again, the faintest stars that can be seen with the unaided eye around magnitude 6 and down to magnitude 32 to the fainter stars that the Hubble Space Telescope has imaged. So it's a scale that's logarithmic. So every difference of 5 magnitudes represents a 100-fold difference. So if it's 10 magnitudes difference, that's a 10,000-fold difference in brightness. So that's basically how the system works. Now, I mentioned that HR diagram before. So what we've got here is an analogue of the Hertzsprung-Russell diagram called a color magnitude diagram. It works in pretty much the same way that you have the color magnitude using the brightness of the star in certain colors, colored filters, which acts as a substitute for temperature. And the absolute magnitude as determined by the Gaia satellite can do this because it can measure the parallax of roughly 1 billion stars. And knowing the parallax, you can work out the true or absolute magnitude of the star. So what these people have done here, hopefully I can make that run again if I go back to it. So this is Gaia measured color magnitude data for several thousand stars. And what you can see here, that Gaia can actually see the pulsating variable stars happening. I'm not sure how well that shows up on YouTube. If you can't see it, jump onto Google at some stage and Google for Gaia DR2 variable star magnitude, color magnitude diagram. So this is you don't normally have ever seen this before Gaia, where the color magnitude, as you can see it actually evolving in real time over a period of a few years. The coloured track showing the different change in temperature and magnitude of the stars. It's pretty awesome. So we move on now to the cataclysmic variables, and we've got a type here called a Dwarf Novae. So what is thought to cause these is that you've got a binary system where a white dwarf is one of the member of the binary. So a white dwarf star is actually a stellar remnant where a star like the sun has evolved, burned up all of its core fuel, starts helium burning, and then when it runs out of helium, it can't burn any more fuel, but there's kind of a last flash of burning that generates enough heat in the core to throw off the star's envelope, and the result is a planetary nebula, which some of you may have seen on a telescope, quite interesting to look at, and it leaves behind a white dwarf, which is a core of basically carbon, a little bit of nitrogen and oxygen, and a very hot and very dense core. The density is hundreds of times that of anything we have on Earth. It's called degenerate matter. The only thing that's holding it up is what's called electron degeneracy pressure. That's a quantum mechanical effect where you can't force any two electrons into the same quantum state, and they resist that with quite a huge force. So it basically stops the collapse of the white dwarf into, say, a neutron star or black hole. That's basically all that's stopping the white dwarf from collapsing, because there's nothing left in it producing heat. It's just its residual heat, except for cases like this where it's in a close binary system with another star, and the companion star has reached to the point where it's getting to the end of its life. It expands into a red giant phase, and the envelope of that star with its atmosphere is growing to such a size that it crosses what's called the Roche limit, which is basically the point where the gravitational force of the two stars is roughly equal. So effectively the star that's in the red dwarf state, it's only tenuously holding on to its outer layers. So it starts bleeding material into an accretion disk around the white dwarf. You get some interesting astrophysical effects where the matter is running onto the accretion disk. You can see as shown in this diagram, you get a hot spot, and these can actually be seen, and they change over time. But it's thought that at some point the accretion disk can become unstable, and it actually suddenly dumps a lot of matter onto the white dwarf, and it generates a large thermal outburst just basically from gravitational potential energy. And this is called a dwarf nova. You'll get a sudden brightening. And these can obviously repeat, because as long as there's more material being siphoned onto the white dwarf. There's another related object called a classical nova. Or classical nova is the plural. So you've got a similar situation, but what happens here is that the white dwarf has gathered quite a lot of this material from the other stuff to its surface until it reaches a point where the unburned hydrogen and helium that it's accumulated on its surface gets to the point where it's unstable. You can get a thermonuclear reaction occurring. Basically, the pressure and temperature is really high on the surface of a white dwarf, as you imagine, has enormous surface gravity. Putting nuclear fuel on its surface, eventually it gets to the point where it detonates in a thermonuclear explosion, and this is called a classical nova. The process can repeat because the nova generates a lot of energy, really bright flashes. We saw with RS Fuiki, which increased by nearly 8 magnitudes in brightness. So many hundreds of times of increase in brightness, and from a thermonuclear detonation. And the material is glowing, really hot and glowing, so it sort of decays in brightness slowly over several weeks and goes back to being a faint white dwarf until the next time. Sometimes they're only ever been seen once. It may be that that's just because it's not acquiring enough matter at a great enough rate, and it may be they only recur every hundreds or thousands of years, so we've never seen those ones recur, but RS Fuiki recurs quite often. There's another one that we saw back in, I think it was 2010, might have been 2011, is T. Pixidus, which was a really interesting one because it was thought that the white dwarf involved was quite massive and maybe approaching what's called the Chandrasekhar limit of 1.4 times the mass of the sun. Although I think that his better data has now suggested that isn't actually right, because its distance isn't what they thought. So the mass is actually a bit lower than was originally thought. But this is believed to be the mechanism of type 1 supernova, type 1A supernova rather, where a binary like this may undergo several recurrent nova outbursts, but each nova doesn't blow off all of the material it accumulated from its partner star. And if such a white dwarf eventually can obtain enough mass where it reaches 1.4 times the mass of the sun, even electron degeneracy pressure is no longer enough to stop the star collapsing. But it doesn't collapse into a neutron star or black hole, because it's being made of carbon, nitrogen and oxygen. The collapse actually triggers the thermonuclear detonation of that material and eventually obliterates the star, and the debris is basically iron and nickel. radioactive nickel, which powers the glow of the supernova for several months as the nickel decays. So possibly if they can accumulate enough mass from their companion recurrent nova, could eventually become a supernova. So and now we get to a supernova. There's the type 1 that I mentioned. There's another type in high mass stars which suffer a core collapse because they can actually carry out the burning of carbon, nitrogen, oxygen, silicon, and so forth in their cores. So basically the core collapses, you get a huge outburst of gravitational energy and neutrinos as the protons and electrons in the core are forced to form neutrons. Now, neutrons themselves have a degeneracy pressure which is much stronger than electron degeneracy pressure. So that allows a neutron star to form possibly up to about 3 times the mass of the sun. After that, there's no known physical process to stop further collapse. So it's believed that if the core mass is more than 3 times the mass of the sun, you end up with a black hole. You can also, I think this was mentioned in a recent talk about supernova, you can have extremely high mass stars. The stars can actually undergo a detonation due to a process called pair instability, which is where the gamma rays at the core of the star start producing electron-positron pairs because of the high energy of the photons. Problem is that without the photons, suddenly you get a massive drop of pressure in the core of the star, you get a sudden collapse. But the material there is still basically not burned, so you get just complete and instant thermonuclear detonation that destroys the star. There's some candidates of those that possibly have been found, but they'll be very rare because only the most massive stars can undergo that process. You also get the thermonuclear detonation of the white dwarf, as mentioned, with the mass exceeding the Chandrasekhar limit. Chandrasekhar was an Indian physicist who first realised that there was a limit to electron degeneracy pressure from principles of quantum mechanics. We haven't had any supernova seen in the Milky Way galaxy since 1604, the Kepler supernova. Probably on average we're overdue for one because they thought to have, on average, probably should occur every 1 to 200 years. It's possible that we've had one on the far side of the galaxy, but couldn't see it because of the intervening material. But we did get one in the nearby Large Magellanic Cloud, which is a satellite galaxy of the Milky Way, supernova 1987A, which had Albert Jones, who was a New Zealand variable star observer, was one of the co-discoverer of the supernova back in 1987. And you can see here some Hubble Space Telescope images showing the aftermath. And what's happening here is that you had a ring of material that was thrown off before the supernova. And the supernova is illuminated at some time after the original explosion, and you can see how the material has changed over time, and you can see the actual supernova debris is starting to race out and hit that in a ring now. Okay. This is another example of a variable star. The thing about these is that they can only ever be observed once, because you're never going to get two stars lining up like this ever again. And the way they find these is massive surveys of stars, usually aiming towards the galactic centre where there's a really large number of stars, so the chances of finding them is much higher. Survey scopes are imaging quite large areas of the sky, and they process these images and look for the characteristic brightening of one of these microlensing events. And you can see here the example where you would expect just with two stars, you get a nice Gaussian curve where the light is amplified by the gravitational effect of the foreground star amplifying the background. But sometimes you get these interesting blips on the light curve, and they're caused by planets that are orbiting the foreground star. Sometimes you get similar effects with a binary, but the people that analyze these can tell the difference between a binary star and a star with orbiting planets. So it's pretty interesting. It shows you here across the top the change in brightness, and you get a deviation where the star suddenly gets unexpectedly brighter again. And Grant Christie, Jenny McCormick, and the guys out at QMU have managed to record these events. So if it turns out to be a planet and you're involved with this kind of work, then you can get your name on a scientific paper reporting the discovery of an exoplanet. So it's definitely something that amateurs can still get involved in. You obviously need a camera, a fairly good astro camera, because some of these objects are fairly faint. Okay, in general, if you're doing variable star observing, there's a naming convention for them. If you see a star that has a Latin letter in front of its name, then it'll be a variable star. So they started off with R through Z, RR to RZ, and so on, till they ran out of those letters. And you can see after 334 combinations, they start using V followed by a number. So if you see your planetarium software is referring to a star like RR Lyrae as an example, as the prototype RR Lyrae star, T Pixidus was recognised fairly early, a cataclysmic variable, actually a recurrent nova. So that's how you can tell in your star nomenclature that they're variables. And there's a couple of examples: R Coronis Borealis, V603 Aquila. I already talked about this, the ranking and measurement of stellar brightness, apparent magnitude. So if you want to work out a 1 magnitude difference, it's actually the fifth root of 100, which you can calculate as 2.512. So the difference of star of magnitude 5 and 6 is roughly 2.5 times. And they use different stars as the reference brightness. Polaris was used originally for this system, but it was found to be a variable, so that didn't work. Vega was set as the 0 point in magnitude. That was also found to be have a small amount of variability. So eventually they gave up on using stars as a reference, and it's now defined in terms of measured flux. This is apparent brightness or apparent magnitude, and with variable stars, a lot of it can be done using visual estimations, but if you do it photographically, There are various different filters you can use. It's quite common, for example, for micro lensing work, that they use a number 12 Ratten yellow filter. Sometimes you might want to use different filters because you can measure the change of colour of the star as well as its brightness. So yeah, if you're getting into astrophotography, you can do these measurements with different coloured filters that can extract different data out of the measurements. And we have an organisation called the AAVSO, the American Association of Variable Star Observers. And the director, Stella Kafka, visited New Zealand a few years ago and did a talk for the society. They basically have databases of observations submitted by amateurs and both visual and photographic and professional observers. So they are the people that maintain the database. They also generate online star charts of these stars, and a lot of information on their website you see here, aavso.org. You can adapt the charts for different field of view. So depending on your telescope and eyepieces you've got, you can find a star chart on AAVSO and use it along with your planetarium software to figure out what stars you'd like to observe that'll fit in a convenient field of view. So I'll just show an example of a AAVSO star chart. So this is for the variable star T Centaurus, and it covers the magnitude range 5.5 to 9. So you can see the stars there. The star of interest is the one with a circle with a sort of reticle marks against it. So what all these surrounding stars are given a number. So these are actually magnitude 6.7, 6.9. So if you were doing this visually by yourself, just looking for an eyepiece, you would look at this star and say, well, it's brighter than this star, but it's fainter than this one. And you use these magnitude estimates to figure out, you're basically bracketing the brightness of the star when you're looking at it. And with a bit of experience, you can get quite accurate estimates of the magnitude of the star. Probably the best observers get down to about 1/10 of a magnitude, which is pretty good for visual observations. Obviously, if you can do astrophotography, then the brightness measurements can be taken off the data off the camera, provided you're calibrating your images correctly. I won't get too much into that, but yeah, if you join the astrophotography group, they talk a lot about image calibration using dark frames and flat frames and bias frames, things like that. Here's another example of the same star, but it's showing a different field of view. And another field of view again, depending on, you basically choose a finder chart that matches whatever combination of eyepiece, or if you're wanting to use these to visually have a look at compare on your photographs before you run them through software to extract the data from the images, you can use these just to get a rough estimate, and also to double check you're looking at the right field, that your go-to scope hasn't put you into the wrong field. And we have a local organisation which is part of a section of the Royal Astronomical Society of New Zealand called Variable Stars South, and they have their own website, which is a good thing to look at, a lot of resources there. If you've got a DSLR, you obviously can't really use, it's not really appropriate to use filters with a DSLR because it's has a Bayer filter built in. So you would only use probably filters with a monochrome camera, which you can turn a DSLR into a monochrome if you remove the Bayer filter, which I believe some people do, but it's then no use as a colour camera. So, but it gives methods of processing data from a normal unmodified DSLR, things like that. So there's a lot of useful articles and resources. Can't really talk about variable stars without mentioning Albert Jones. I mentioned before he was actually the guy who co-discovered supernova 1987A. In 1963, he was the sixth astronomer to make 100,000 variable stars observations, and before he finished, he had made well over 500,000 observations. So, pretty remarkable achievement. And he was often an accuracy of 10% in brightness, which is pretty exceptional. He's also discovered Comet C 1946 P1 Jones and co-discovery of the Comet Sayugo Utsumiyama Comet C 2000 W1. And Albert passed away a few years ago, but it's pretty famous in New Zealand amateur astronomy circles. Talked about photometry for variable stars. The common method of doing photometry is to use the UVB system, ultraviolet, visual, and blue. So these are standard filters you can get. There's a more modern set, I believe, that uses the Sloan set. Some of these filters can be quite expensive for high quality ones. Obviously, as I mentioned, the filters you use are with a monochrome camera, either a modified DSLR or a specialised monochrome astronomy camera. So a DSLR with a colour sensor can still use it, but you don't use those with sensors. And if you're using a DSLR, the sensors are generally larger, not always with the newer ones than the dedicated astronomy cameras. But if you're just using a lens rather than a telescope, you're going to be capturing a really large number of stars, and there'll be lots of variable stars in that image. And of course, you have to use raw images off the camera, not JPEGs, to get sensible scientific data. Okay, so that's the end of my talk for today. Chris is back next week with the normal introduction to astronomy program. It'll obviously remain online. The monthly meeting talk we're not sure about. We've got somebody who may be able to do it, but we may have to move them to another date. So we're just waiting for confirmation of that. And for the practical astronomy, we're going to do our spring night sky talk on the third Monday of the month, but that will be done online using online rendition of the night sky using something like Stellarium or other astronomy software. So are there any questions before we finish?
None so far. I've just asked our viewers if they have any, and there's probably just a minute to ask some if there's any burning questions about variable stars. I thought that was a super interesting presentation. I'll just add, if anybody is interested in the gravitational microlensing that Bill was talking about earlier, then do get in touch with either myself, Steve, or Jonathan. And once we're able to go out to the observatory again, our Kumio Observatory is involved with gravitational microlensing observations. And if you want to see how that's done or get involved in the observation team, then please do let us know.
Yeah, it's not restricted to gravitational microlensing, but over the winter months that has priority. But there's other things you can do as well if involving variable stars or just learning how to do astrophotography to become part of that team.
That's right. We've got a very good astrophotography camera and a 16-inch scope. So
And
do
with
let us know.
a wide selection of filters, I believe, as well.
We do indeed. Still no questions, so thanks very much, Bill. It's probably we can leave it there.
Okay, thanks, Steve. And the storm didn't cause us any power loss, so that was a good thing as well. Okay, thanks, Steve.